Greetings, students. Welcome to Screencast number 2. This one, the topic is rational exponents, something we started learning about. Well, it also has to do with something called Kepler's formula, which, as you can see right here, is d is equal to 1.82 times r to the 2/3 power. 2/3, of course, being the rational exponent because 2/3 is a rational number. Remember, a rational number is any number that can be written as a fraction, and clearly 2/3 can be written as a fraction because it is. All right, well, who was Kepler and what was the deal with this formula? First, let's learn a tiny little bit about the man Kepler himself. According to this NASA website, which I found, as you can see, his first name was Johannes Kepler, and he was a wonderful mathematician and astronomer that did a lot of good. As you can see right there in the first paragraph of his biography, he was born December 27th, 1571. As you know, that was a long, long time ago. And look at all the things that Kepler did. First, to correctly explain planetary motion, thereby becoming founder of celestial mechanics and the first natural laws in the modern sense, being universal, verifiable, precise. And of course, as you can see down here, he actually did a lot more than just that, but he was a very, very wonderful astronomer and mathematician. And we're going to use his formula right here, right now. So, you can go to that website on your own, of course, but here's your problem. Well, here's the first problem that I'm going to present to you, and I'm going to help you to solve. It says to use Kepler's formula, which as we can see is right here, which gives the average distance, d, in millions of miles of the sun from a planet with a period of revolution in r in days. All right, so this one has to do with exactly what Kepler was studying, planetary motion of celestial bodies. Well, so let's do this. The formula is d is equal to 1.82 times r to the 2/3 power. So that is a very, very important information. Let's write that down because it is a formula. D is equal to 1.82 times r to the 2/3 power. Now, as you can see right here, let's make this a better 8. As you can see right here, we have two variables, the first one being d and the second one being r. All right, now what is d? Well, d is a distance in millions of miles. So we'll put that down there, million miles. And r, of course, is in days according to this formula as we see right here. Days and millions of miles. So d is a distance and r is a period of time in days. That's going to become is very important when I present to you your problem. Now the problem presented is Venus orbits the sun every 224.4 days. We have to find the distance from the sun to Venus to the nearest million miles. Well, they gave us one number, 224.7 days. So therefore, is that d or r? Well, clearly it is r because r is in days. So let's fill that in, 224.7 in days. Which means we are going to replace r with the number 224.7. So let's do that. So d is equal to 1.82 multiplied, there's the dot, by 224.7 to the 2/3 power. So as you can see, we have replaced r with 224.7 to the 2/3 power. Now, the question is, how in the world do we handle something to the rational exponent of 2/3? Well, of course, we know order of operations says to tackle the exponent first. We have an exponent. It just happens to be an annoying rational number. No problem. We can handle it. As you can see right here, I have restated it. We have replaced 224.7 with, we've replaced r with 224.7, as you can see right here. But I want us to see what we've done here. Remember, what we learned in class is that all you need to do is change 2/3 into two different exponents, because we know 2 multiplied by 1/3 would still give us 2/3 in the end. As you can see here, I've taken this 2 that was in the numerator and boop, off with its head. It's come off. And now we've rewritten 224.7 to the 2/3 power as 224.7 to the 1/3 power to the second power. Because as we know from the the product rule of exponents, is that if you have a power to a power, you multiply them. So if we were to multiply this 2 back to this 1/3, we would get back 2/3. So yes, this right here is definitely equivalent to this right here. Now all we have to do is simply enter this into our calculators. Okay, so how do we put in a 1/3 into our calculator as an exponent? Watch this video here on the right of the calculator doing it. I'm going to press in 224.7. Now, the exponent button is the caret button, and as you can see, I must put my 1/3 into parentheses. And if I do that, as you can see, I get 6.07949, blah, 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 blah. That huge digit right there, that huge number right there, which I don't want to write down on my page. So we're going to use the powers the calculator has given to us, okay? The ability that it has to simply keep that number in there, and as I keep pressing the certain buttons, it will only use that entire number there so I don't have to retype it. So I've now raised it to the 1/3 power, and it's 6.079497592. I now have to square that, and I don't want to have to re-square it, or retype it in. So I'm just going to hit answer, and then squared. And as I do that, I notice that I get 36.96029098. Okay, good. And now once all is said and done, I have raised it to the 1/3 power, then I've squared it, I'm done with my powers, and I have to take that 36.96 number, and I have to multiply it by 1.82. And then upon doing that, again, notice that I just hit times, and it gave me ANS right here. That means whatever was in the previous display is now right there in the answer. Just like 6.0794, all that, when I just hit squared, that made it into the answer. Think of ANS as a variable, and whatever was the previous display is now entered into ANS. So the answer, which was this 36 number, times 1.82 gives me that, 67.2677298. Okay, well, that's really good to know. But now my question is, how do I state that? Well, look at the question itself. It says, find the distance from the Sun to Venus to the nearest million miles. In other words, estimate it, round it to the nearest whole mile. So let's do just that, in fact. 1.82 times, it was approximately 36.96. And then 1.82 times whatever this 36.96029098 number was. We multiplied that, and as you can see, we got 67.2677. Okay, well, you know what? We don't want that because it says to approximate to the nearest million miles, which means 67.26, or just 67.2, roughly estimates to 67. So is that 67 miles? In other words, the distance from the Sun to Venus is 67 miles. That would be pretty cool. You could just jump in your car and get there in like an hour if you go fast enough. No, of course not. D was not in miles, it was in million miles. So here's our answer, 67 million miles from the distance to the Sun. Kepler used this formula so that he could calculate the distances between celestial bodies, planets, stars, suns, things like that. Pretty intense, especially for someone who was born in the 16th century. Amazing. Amazing. So we have our answer here. Okay, now your question is the following. All right, so here's your problem. It says Jupiter is about 484 miles from the Sun. Estimate Jupiter's period of revolution in years. This question, while it does use Kepler's formula, is slightly different than what you just saw me do. Nevertheless, it does use the same formula, only they give you different information and you have to solve for the other variable. You see, what the information gives you is Jupiter is about 484 million miles from the Sun. Remember, D was it in millions of miles. So they're not giving you R, the number of days. They're giving you 484 million as D, which means you are going to have to take 484 and send it into D, and you're going to have to solve for R, because R is now unknown. Now this is a little bit more challenging. Doesn't mean you can't do it. It means you have to use the powers of algebra that you already have in you. Now here's one more thing to mention, okay? Keep in mind, R is in days. So once you calculate R, you're given a number, and it's going to be a big number. If you calculate correctly, it will. It's going to be a big number, but that's the number of days. The question is not asking for period of revolution in days. It's asking for period of revolution in years. So you have to take that big number and figure out how many years is that big number, because it's in days. Okay? So again, this one's a little trickier. Doesn't mean you can't do it. Just means you might have to ask a question or two here and there, and I'd be more than happy to help you. Or you can email me. I am looking forward to your responses, of course, and we will review next class what the correct response, the correct solution was. Remember, your submissions could be many forms. You can do a written response. You can do your own screencast, which a few of you did, which is fine. You can make your own little video. You can make an audio recording. I'd be happy to listen to that. You can really do anything. The possibilities are endless. You can even make a Vine. I'm still waiting on someone to make a 6-second response video to one of these screencasts. That would be really cool if you can do that. Okay, a little bit challenging, but can be done. Well, that's up to you to tell me. Anyways, hope you enjoy this one, and good luck.